Hello. So today we will be covering Linux system calls. We are in the operating system module and we are in lecture number 2, Linux system calls. So in the last lecture on Linux architecture, we understood that as a user in the user space program, you want to access services that the kernel provides, you need to make system calls. So you're running a program and you want to access kernel services, you make them through the system call process. You could be writing something standard out, you could be creating a process, you could be asking for memory, you could be asking for making a file IO operation or a network operation. For all of these and more, you make a system call to the kernel. So where are these system calls defined? In Linux, and we will be discussing 64-bit, 32-bit version is a little different. So there are around 380 system calls. That is the total set of system calls that you can call. Now, the way you make a system call is in assembly, we had the instruction syscall and sysret. We went through that in the last module. So you use those instructions. When you call those instructions at the end, the Linux kernel is listening. So that is how you make a system call. You'll make a system call by calling syscall. And then you tell which system call you want to make. Every system call has a system call number. For example, read is 0, write is 1, exit is 60. I've put just a few system calls here because we'll be using some of these. Every system call also has defined its set of parameters that it takes, the arguments, and what it returns back to the user of the program. It is like a function call. If you want to know more about all the system calls, you can look at the system call table. I've also put a link below on a nicer representation of the system calls with the arguments that these system calls take. Now, before we get back to programming in assembly and making some system call, there is something important to talk about, and that is the application binary interface. Now, if two functions have to be able to work with each other, then they are sharing the registers, and there has to be some kind of agreement in what registers are available to whom. And function calls, A can call B, a function B can call C, function C can call D. So in this whole cycle, there has to be some level of understanding who owns which registers. We will divide it by the calling function, which is the caller, and the called function, which we call the callee. We also are looking at the general purpose register set, RAX through R15. There are registers that the callee or the called function is supposed to keep as is. They need to preserve those registers. And the column here that says callee required to preserve register talks about those explicitly as they need to be preserved. The other registers are at the discretion of the callee. You can change what is provided to you. There is also in a parameter passing agreement, an argument passing agreement, when one function calls another function, the calling function is calling the called function, it will pass arguments and it will get a return value back. So which registers are used for passing the arguments? Now, there are 6 arguments that can be passed through registers, and they are written here in the purpose column. The first and second function arguments are passed in RDI and RSI. The third and fourth function arguments are passed by RDX and RCX registers. And the fifth and sixth function arguments are passed by the R8 and R9 registers. The return value is passed back in the RAX register. Now, note that because I'm passing a function argument doesn't mean that those are owned by the caller. You can pass the arguments and the callee function can get those arguments and you still use those registers in however it desires. Also, not all function calls take 6 arguments. If they don't, then you simply don't use those arguments. If you just pass one argument, you will just use the first argument, which is the RDI register. That's it. Now, what if you need more than 6 arguments? The way you pass more than 6 arguments is by passing them on the stack. So the stack is where the other data will be passed instead of the registers. Now the stack is in the memory, so it takes longer to retrieve that data, but it is available for all larger set of arguments that don't fit in these 6 arguments. Now, how does this convention apply to the system calls? So system call arguments use the same convention. They just have one difference. They use the register RAX to give the system call number. Because the system call is called in a unique way using the syscall instruction, the RX register carries the system call number. The rest of the arguments 1 through 6, use the same standard registers. And after that, after 6, you would pass them additionally through the stack. The return value will again be passed through RAX as a standard. Now let us look at an assembly program and see how this applies. We will go back and we will now make our assembly program a little bit more complicated. Let us add one more function call. So we will go to the Hello World program, and I called it Hello 64 because it's our 64-bit assembly language program. So as we talked about system calls, the user space is where Hello 64 will run. Hello 64 is going to make a system call. It wants to write Hello World to the standard output on your screen. And to do that, it needs to make a kernel system call. It is going to make the write system call for that. At the end of the program, it also wants to exit the program. So it will make a second system call at that point, which is the exit system call. The exit system call will exit the process. Now we compile this with NASM, and I talked about it in our first assembly language programming. Then we link it and /hello64, call the program, and you get back Hello World. Now on the right side, I have the source code for it. Let us see what made Hello World appear. And in assembly language, the source code is not too big. It is pretty smallish. Now we can see that to make the first system call to write Hello World out, you need to use the write system call. And we can see in the specification that write takes 3 parameters. The first parameter is the file descriptor. The second parameter is a pointer to a buffer where the string will be written that we want to write out. And the third parameter will be the count, the size of the write operation, the length of what we are trying to write. It also returns back one value, and that is the size or the number of bytes that were written. Now we can ignore that return value. So let us see what we did. We moved, we have some constants defined. The hello world is a constant string defined in message, and you can see that in the bottom .data section. We also have the length defined, and the length is equal to the hello world, length of the characters there. So as we go top down, the first line says move rdx comma len. We are copying length into rdx. Now keep in mind rdx takes the third argument, and in order here, as the function call expects, the third argument goes to rdx. Then we will pass the message pointer. That we will copy to RSI. So in argument 2 is passed to RSI register, we are passing the pointer to where the message is written, the string, to RSI. And then we are doing a move RDI comma 1. RDI takes the first argument, and the first argument is the file descriptor. Now for standard out, the only file descriptor that we need to use as convention is 1. 1 means standard out. Then we also have to provide the system call number that we want to make. in this case, we reviewed just in the previous slide, the system call for write is system call number 1. So we will pass 1 to the RAX register. Right after that, we will make syscall. Now, syscall knows everything because everything was passed to it in the registers. So it is going to, the kernel will get the call at that point. It'll do the write operation and come back at this at the next instruction. So what is the next instruction now? We are going to make the exit system call. Now, the exit system call just takes one parameter, the status, and it doesn't have any return value. So one parameter means one argument, and argument number 1 we pass to RDI register. So we are doing a move of 0 to RDI. Then the system call number needs to be passed to RAX. The system call number for exit is 60. So we will pass 60 to RAX. Then we make a syscall. And voila, that is pretty much the code. We had hello world written out and we exited the program. So how do we know that this actually all this happened? Well, there are some debugging utilities you can use, and STrace, which is system call trace, is one of those. It is a very useful utility and we may as well practice it here. So if you call the program using STrace and /hello64, it will tell you all the system calls that this program is making. And we can clearly see here the first system call is an execve. Now we didn't call it, but we will cover it in the next lesson. Execve is just the call to change the program to run hello64 program. Now that the hello64 program is running after the execve call, the next system call is write, and you can see the 3 parameters. We passed 1, hello world, 14 length, and then the return value is at the end of the line equals 14. Then we do an exit with a status of 0, and then the program exited. That's it. STrace also provides you another, and you can use parameters to see what all STrace can do. It's a very powerful tool. There are many more. The one that I want to show you now is you can use a -c to get statistics. So maybe you are not interested as much in the detail of every system call, but you want to know the statistics of how is your overall program running? What system calls is it making? And how long do they last? How long do they take? So you can run an STrace with a -c and it will give you those statistics. The timing of the system call, the calls per second, per microsecond in this case that you're calling, the number of calls with errors back, and which system call. And then it gives you a nice total. So the total we get is 2 system calls, 1 write, 1 execve, exactly what we got on the top, but in a nice statistical format. Now, this is useful because when you run a real system with a lot of calls happening, to be able to get the first view is going to be hard, so you may want to start with a higher level statistical view. Now, we have done and gotten an understanding of assembly language, and that was important to understand at a low level what is happening. But we don't really write code in assembly language, so we write code in higher level languages. Now in this course, we'll use a lot of C programming, and C provides libraries that make it easier to write code, and the C compiler is going to generate the assembly code, the operation code that will be run. So let us start by doing a hello world in C. And here is the program. Hello_C is the executable. It has a main function, and that's standard in C. You need a main function. And in the main function, we can see on the right side, we are making a printf call with hello world. And then after that, we do a return 0. And that's it. There is 2 lines of code there, the print and the return, and both are system calls. So how does this end up? Well, printf is the standard C is a standard C library function. That function is going to call the syscall write that we just did. Now, let's look under the hood of this function using STrace, what it really did when it came to the system call interface. So here is an STrace of hello_C. And let us do a statistical STrace first to see how many functions were called. And we can see there were 26 function calls made. Now, keep in mind that as you go higher, when we had our assembly program, we created it just for the function we needed. So it's very optimal, very optimized to what we want to do. In C, even the basic program will get a little bit of memory going on. It'll open up some file and load up the program. So there are a few more system calls that get made in C. But at the end, the ones that we cared about in our program are still the same write that we did. And we got 26 system calls. Now I have also done an STrace output, and I didn't put the whole output because all the system calls don't fit in the screen, but you can try it yourself and see all the system call details. You could see here also that we do have an exec VE call, which means that is the call that loads the program hello_C to be run. Then we do have a write call here, which will do the standard out write. And you can see the parameters are exactly the same. And then we have an exit. So this is the same hello world program we wrote in assembly language, now written in C language. So that was the introduction to system calls. And in the next lecture, we will be covering Linux processes. Go enjoy and code. And I have also put my code on github.com. If you want to see the examples that we covered here, you can go to the Under the Hood repository and you will be able to see the examples there. I have also published the course catalog with links over there to that GitHub. You can also subscribe to the YouTube channel for the next upcoming videos. Thank you.